Imagine a graphene mesh megastructure rising 30 kilometers into the atmosphere. At that altitude, gravity is only one part of the engineering equation. The structure must survive constant, extreme fluid dynamics from atmospheric wind currents. Standard codes, like ASCE 705, treat wind as a static pressure against a rigid object. On a hyper-tall structure, this math breaks down. The massive surface area multiplies the force. Under this static model, the sheer tonnage would instantly snap the foundation. Structural survival at this scale depends on managing dynamic movement. These structural oscillations create kinetic loads that static pressure models are inherently incapable of accounting for. At extreme heights, a super-tall building does not behave like a rigid box. It behaves like a highly flexible cantilever anchored to the earth. This introduces aeroelasticity, the complex interaction between the aerodynamic forces of the wind, the structural inertia of the building, and its elastic material forces. As wind pushes the structure, it bends. This deformation instantly alters the local airflow. Air must compress and accelerate around the newly curved profile, generating self-excited aerodynamic pressures. This feeds back, pushing the tower oppositely, inducing a perpetual loop of structural vibration. Mathematical models are blind to this fluid-solid feedback loop. They cannot reliably predict how a specific shape will alter the air currently pushing it. Mapping these limits requires physical, multi-degree of freedom empirical testing. To measure this feedback loop, researchers utilize a closed-port boundary layer wind tunnel. The test section spans 15 meters in length, providing enough physical space for airflow to stabilize and interact with the subject. The subject is a 1 to 350 geometric scale aeroelastic model of a super-tall building. Crucially, the aeroelastic model is completely unconstrained, allowing it to flex, bend, and twist freely on its base. To capture the precise aeroelastic interactions, the model is wired with a dense instrumentation network. Multi-level laser distance sensors track exact physical displacement, while 120 individual pressure taps record real-time surface wind loads. The researchers first establish a baseline using an entirely uniform flow field. The wind velocity is flat, consistent, and smooth across the entire height of the tunnel. Then they introduce the experimental condition, an atmospheric boundary layer simulation. By utilizing passive turbulence generators like spires and roughness elements, the tunnel replicates terrain C, the highly chaotic, turbulent wind field of a dense city. This chart plots structural height against turbulence intensity. In the urban terrain simulation, turbulence is dense at the base, gradually smoothing out higher up. We target critical wind velocities, locking in on 8.5 and 10 meters per second thresholds to trigger physical responses. By combining a turbulent urban wind profile with a freely moving aeroelastic model, the sensors can finally record true coupled torsional and lateral motion. This graph maps fluctuating displacement for the uniform flow test. As velocity increases, sway normally rises at a steady slope, but we see massive, isolated displacement spikes occurring explicitly at 0-degree and 90-degree attack angles when wind hits the building squarely. Severe, violent lateral movement pulls the building side to side across the wind, generating forces far more destructive than the direct along-wind push. The fluid mechanics driving this extreme lateral movement are known as vortex-induced vibration, or VIV. This top-down visualization shows vortex-induced vibration. As uniform air hits the building, it splits, forming low-pressure vortices that alternate shedding from the sides. Each shed creates a sudden pressure drop, pulling the structure into a vacuum, violently whipping the building side to side. If the frequency of this alternating vortex shedding aligns perfectly with the building's own natural resonant frequency, catastrophic narrowband resonance occurs. The building absorbs the energy, amplifying its own sway until structural failure. Here is the displacement data recorded during the highly turbulent Terrain C urban simulation. The plot shows a smooth, consistently rising curve. The catastrophic resonance spikes from the uniform flow test have completely disappeared. High-intensity environmental turbulence, chaotic, messy wind, acts as a protective dampener. The atmospheric noise inherent in an urban setting effectively breaks the rhythm of regular vortex shedding. In a dense city, the wind is full of small-scale, chaotic vortex clusters. This interference prevents the formation of the large, perfectly synchronized vortices required to pull the building into a resonant sway. These power spectral density graphs map kinetic energy. Left is uniform flow with narrow peaks. Right is turbulent flow with broad mounds. The total energy is strictly conserved, but instead of a single lethal frequency, it redistributes into continuous multi-frequency structural vibrations. Urban turbulence prevents acute catastrophic resonance. However, it subjects the building to continuous multi-directional vibrations. Engineers must design these structures to withstand decades of relentless broadband fatigue. Aerodynamic power spectral density graphs across 3 axes map these loads. A massive primary energy peak dominates the crosswind spectrum, the lateral movement, but distinct secondary peaks echo across the alongwind and torsional spectrums at precise intervals. This is the empirical signature of bending torsion coupling. When wind forces the structure to sway laterally, its own inertia and elasticity force it to twist and resist in entirely different planes. Alongwind resistance is driven by mechanical forces that originate far behind the front face of the tower. The secondary alongwind peak appears at exactly twice the lateral frequency. This occurs because the building experiences a drag pulse on every half swing, once when swaying left and again when swaying right. This specific synchronicity proves the 2 motions are mathematically inseparable. A super-tall building actively generates a massive percentage of its own structural resistance load purely through its own lateral movement. Designing for this requires a holistic approach, where every geometric axis is evaluated as an interconnected system. If we extrapolate this data back out to the speculative 30-kilometer graphene mesh megastructures, the atmospheric dynamics dictate the exact limits of the design. The empirical wind tunnel findings do not scale linearly. They define specific aerodynamic zones the tower must traverse. At ultra-extreme altitudes, the peak of the megastructure will completely exit the dense, chaotic, and protective turbulent boundary layer of the Earth's surface. By breaching the upper atmosphere, the top of the megastructure re-enters conditions of smooth, uniform flow. Without urban turbulence to break up the airflow, the peak is exposed to clean, perfectly alternating vortex shedding, and the risk of catastrophic vortex-induced vibration returns. Any future megastructure must utilize sophisticated dynamic dampening hardware explicitly because it spans 2 entirely different fluid dynamic realities. It faces broadband fatigue in the turbulent base and severe acute resonance at the uniform peak. Pushing the boundaries of extreme vertical design requires looking past static material strength. The true test is mastering fluid structure coupling. The atmospheric boundary layer demands a compromise. Turbulence eliminates the acute resonance of uniform wind while increasing the continuous, multi-frequency vibrations that lead to long-term material fatigue. If a civilization scales this concept to the level of an Ecumenopolis, a planetary city with interwoven, high-capacity foundation piers resembling mechanical tree roots, architecture and atmosphere completely merge. The physical geometry of the cityscape dictates the weather, and the weather dictates the structural load. The ultimate frontier of structural engineering lies in abandoning the attempt to rigidly resist the wind. Instead, the architecture of the future must actively harmonize with the aerodynamic feedback loops of the atmosphere.